Hi, hello guys. Hey, it's Seki. So once more, I always apologize for coming after several weeks, if not months. But someone, I think 3 weeks back, sent this question, and it's a question. It's a question of symmetrical faults. Symmetrical faults. Normally in practice, it's very rare that a symmetrical fault will occur. Actually, it doesn't exist. But they just show you as to what impact they would bring into the power system. And they are it's actually the types of faults that an engineer don't want. Most faults that exist in practice are of an unsymmetrical, are actually unsymmetrical in nature. And then symmetrical faults are just, we are just doing them for you to show what a serious impact they can do to the power system equipment and the damage to the elements of that particular power system. Symmetrical faults, well, if I may quote from say for instance elementary books, it is actually that fault that gives rise to asymmetrical faults. By symmetrical faults we meant how to put it, that faults that give rise to 102 with three faces being 120 degrees apart, and then when they are brought together under fault conditions, they are brought simultaneously together. That process is called symmetrical faults. And you'll see normally it's something like these are three faces, they are added together under symmetrical fault. This is a fault. These three conductors are brought together as if you've got this line system, for instance, this line system, let's say for instance these are the currents IR, IY, I blue, IY, IR, IY. This is red, yellow and blue. Those are the lines, those are the three lines of a power system. And then here of course you'll have a voltage. This one is connected to IR, therefore it's VR. This one of course, sorry, is connected to VB, so is VB is connected to the blue line. And then this one of course is red, yellow. Okay, this one is yellow, but you can see basically what I mean. They are very it is a very dangerous short circuit system. But the reason why I'm here today, someone sent roughly 6 problems. I can't make 6. So today, for instance, I can only make 2. And then probably tomorrow, my brother will help me to do another 2. And then it says what? It's important that as we do problem that you listen properly, because most of the information you're gonna get it through listening as I write and so on, because most of the time we don't have time. It takes a lot of data, guys. I've got a small space. I think this is a 30 to 40, if not even 50 minutes problem, but it's very important. It says a 3-phase 20 megavolt amps alternator has internal reactance of 5% and negligible resistance. Find the external reactance per phase to be connected in series with the alternator, so that the steady current on short circuit, very important, does not exceed 8 times the full load current. What I want to mention here before I continue, the modern power system equipment. Let me do this. Let's say for instance this is an alternator, and then the alternator normally it supply the bus bar. This bus bar maybe is gonna be a transformer, is gonna be connected to it, and then that line is gonna have a certain rated voltage, let's say 10 kilovolts, and then of course it will have other elements such as the resistance, the reactance, up to a certain point of fault. It depends where the fault occurs on this line. But the point I want to say, sometimes we put a reactor there. A reactor, it is actually a coil with a number of turns, so that designed to have large inductance, but that inductance, it should be more larger than its ohmic value or ohmic resistance. However, in practice, it is not a common practice to put in a reactor. Why? Most equipment are built and fitted, are built with sufficient reactants to protect themselves from short circuit conditions. But unfortunately for this problem, you are requested to calculate that should a need be to put a reactance in series with the alternator. What will be the value of that particular reactance? That's the question they are actually asking. So I'm going to help you to get this. You can only find this, I think, I will say, for instance, in books. In practice, we normally don't put in reactors because they've got sufficient built-in reactants to protect themselves. That's basically the case. So we are given this. And what else? What else is given? Has an internal reactance of 5% and find the external reactance per phase to be connected in series with the alternator so that the steady current on short circuit does not exceed 8 times the full load voltage, the full load current. We are also given the current there. So we know that the apparent power is equals to √3 V line I line. This is the line current or load current. Therefore, this, or let me say the load current already, is equals to what? Is equals to 20 megavolt amps, can be written as 20 times 10 to the power 6 in terms of volt amps. All over √3 multiplied by 10 multiplied by 10 to the power 3. And it is equals to what? It is equals to, and then guys, please, whatever I'm doing, if need be, write it down, because as you can see, I'm not gonna have space. This is a very, very long question. By the look of things, it's a very, very long question. And it is 20 exponent 6 divided by open brackets, second function, square root 3 times 10 exponent 3, closing brackets. Answer. We've got what? We've got 1154,7 amps. Why? We converted the megavolt amps and kilovolts to normal basic units. So this must be in a basic unit, and that is amps. But now, if you read this statement carefully, you are told that the short circuit current should not exceed 8 times the full load current. Therefore, the short circuit current stand to reason thereof is equals to 8 multiplied by 1154,7, and it is equals to what? It is equals to 8 multiplied by 1154.7. Answer 9237.6. It is equals to 9237.6 amps. As you can see, the short circuit current will always be larger than the full load current. This is the rated full load current when no fault exists. But the current, when a fault occurs, the current rises to a dangerously high value, as you could see. 9,237 is far bigger than 1,154. So it raises to a highly dangerous value. And the impedance of the system, as maybe I will draw this now, the impedance of the system, it becomes smaller. But that impedance is the one that should oppose the short circuit current up to a point of fault. It won't make sense, but I will show you now. So basically this is, okay, van Strayer, this is 11, I load is equals to 1154.7, and then short circuit current is equals to what? 9237.6 amps. Okay, I'm just writing them down in case a need arise that I should erase. Then I know I've got the calculated information. Now then that I've got that, remember you are requested to calculate the external resistance. The formula for the percentage reactance, X stand for the percentage reactance, is equal to what? Is equal to the S base is normally given. So here, this 20 megavolt amps, it is still a base. Why? There is no any other ratings of equipment. We've got only one alternator rating, and that is that, and this is our base over the percent SB over what? Over 10 multiplied by 10. Okay, V B squared multiplied by X. This is an ohmic value, the reactance. Multiply by 100%, of course, but that will come later to make things short. Basically, this is the situation. But this will come later. I just want to show you what's going to happen there. Another formula. We have calculated the short circuit current as the load current multiplied by 100 over the percentage reactance. This is the basic formula. But when do you use this formula? You only use this formula only when the reactance, it is the only element in the power system, and you are told it is the only element because they told you that the resistance is negligible. I don't know whether it makes sense, Mr. Kisana. It should make sense. Right. You are given this. You have to find this first. You are requested to calculate the reactance. I showed you the formula earlier, but we're going to come to that one. All right. This is 9237.6 is equal to the load current of how much? 1154.7 multiplied by 100 over the percentage X. Like I said, that you should always listen. Normally, we always in the power. This is the principle of power system protection. We always prefer to do calculations in per units or in the percentages. Why? They allow the engineer or people in the field to be able to do rapid fault calculations easily. Why? The transformation ratio normally is difficult to use transformation ratio because the system becomes unstable. You have to multiply by the square or divide it by the square of this or the square of that of K and so on. That makes the situation very difficult. So normally in practice they prefer that you use per unit or percentage, the percentage reactance. We have to find this one. Let's divide by this one. We've got 37.6 divided by 1154.7 is equals to what? 100 over percentage X. Is that correct, Mr. Kisana? It should be correct. Now, let's multiply by 1 over 100 on both sides. Why? To get rid of this. And then we are left with what? 1 over percentage x. Let's find out what's going on there. Okay, let's say this is 1 over percentage x is equals to 9237.6 all over 100 multiplied by 1154.7. We can cross multiply, but without cross multiplying we can safely say percentage reactance is equals to what? If we multiply this, is gonna be 100 multiplied by 1154.7 divide by what? Divide by 9237.6. Therefore percentage x is equals to what? Look. Gentlemen, look, I've cross multiplied this multiplied by 1, this multiplied by that, this multiplied by 1 is that, and then I divided by this one to make this one subject of the formula. And then it's equals to what? It's equals to 100 multiplied by 1154.7 equals to divide by 9237.6 is equals to what? 12.5. It is equals to 12.5%. Why percent? Remember, the 100% was already in. We cannot multiply by 100%. It was already there. We've got 12.5% reactance. All right, 12.5 reactance. Percentage x is equals to 12.5% rather. Sorry. Gentlemen, allow me to erase. I've got that. I've got this. Okay, right. This is very easy actually. It's just that they are long. But my head is against the wall. I'm forced to do it. Okay, right. We've got, we calculated 12.5. Therefore, we've got what? Percentage x external. Let's use it external. The percentage, not the reactance, the percentage reactance is equals to what? 12.5 minus what? Minus -5%. Minus 5% is equals to what? 7.5%. 7.5%. Now we come to that initial formula that I showed you earlier. Why? Because we now have to calculate the external reactance. I will say percentage x external is equals to what? Is equals to S base over V, let's say VB squared multiplied by X, which is the reactance in ohmic value, multiply by what? Multiply by 100% to express it in percentage, of course. Now we've got what? This is calculated and found to be 7.5 is equals to this. The only equipment, the only megavolt amps in the system is 10 multiplied by 10 to the power 6 all over 10, this voltage of the line, 10 multiplied by 10 to the power 3 squared multiplied by what? The required x multiplied by 100%. Okay, right. First, let's divide by this 100. We're gonna get what? We're gonna say 7.5 divided by 100 is equals to 0.075 is equals to 10 to the 6 divided by 10 multiplied by 10 to the power 3 multiplied by x. All right, guys, I'm gonna, okay, this is squared there. This is the formula, guys. Don't ask me where the squared come from. We can even prove it to you just after this to show you where it come from. I'm just gonna cross multiply by this. I'm gonna 0.0775 cross multiply I multiply it by 10 exponent 3 squared, I divide by this to get x. Let's do it. I cross multiply. Remember, everything in life is over 1. So it is equal to 0.075 multiply by 10 exponent 3 squared is equal to what? 7.5 million. Okay, now let me not go there. Divide by 10 exponent 6. Answer. Did I square it? 0.075 multiply by 10 exponent 3 squared. Answer. Divide by 10 exponent 6. So much. We've got x is equal to 0.75 ohms. Does that make sense, Mr. Kisana? This is 0.75%. Okay, it's percent. SB over VP squared. 10 to the power 6, 10 exponent 3 squared. This should make sense. This should make sense, I think. This should make sense. But guys, basically what I want to tell you, the honest truth, this is actually the procedure. But when you calculate the problems of this magnitude, I would prefer that you always draw the line diagram. You at the mines, or actually anywhere in the power stations, there must be a line diagram of the power system. In the substation, there must be the reticulation of that particular power system to that particular station. And remember, there are a lot of things. There must be fire extinguishers as well. There must be what? The switch gears must be numbered properly, and there must be closed at front end. You know what to do. You must open the door when you arrive at the substation. Why? There must be 2 people as well. Why? In case of emergency, there must be many ways to escape. Anything can at the substation, anything can happen. But basically, this is the case. I once did this problem, guys. I think I've got 0.3 something here. Just go through it and check what mistake did I do. But we're still gonna do. I will come back to you and tell you what's the problem. But this is the procedure. We are definitely sure this is the correct answer. We're gonna do another problem now, guys. Just now, and I think that one probably is gonna need the line diagram. I've got it in my hands here. It's written here. But thank you very much, man. Please, guys, subscribe, man. Subscribe, share this video, like it, share it with your friends. I know, man. Just view it until the end. It might help you. But thank you very much, man. Nah, sure.